Netlist enabled emulation platform for accelerated K-level verification. Abstract. Conventional simulation environment follows register transfer level RTL based design approach for the verification of SoC chipsets, as it offers more granularity and profound insight of the design. But this type of the verification approach is vulnerable in identifying the delays and switching the activity for power estimation. Hence, in order to tackle these kind of the potential issues, Gallagher simulation is employed to evaluate certain intellectual property (IP) features of a system-on-a-chip (SoC). However, it is tedious and time-consuming, as the verification of a single scenario takes weeks to complete in a Gallagher simulation GLX environment. Gallagher emulation (GLE) approach is efficient and effective as the emulator runs on the actual hardware. Driver clock frequency is in the range of MHz as opposed to the simulation, which is in Hertz range, thus making the execution and validation time faster. The verification result obtained is more accurate and reliable as the emulator is close to the actual silicon. In this paper, we will delineate the techniques of integrating the Netlist design files and the emulation environment, validate a set of use cases, and compare the results with the simulation-based verification. So the verification time is significantly improved by an order of 70 to 90 times in the Gallagher emulation. The emulator on which these scenarios are executed in Synopsys GBoo. Chapter 1 Introduction. As the complexity of design is increasing rapidly across various SoCs, the time to market of the chip is also getting delayed, and the validation of SoC chips after the silicon tape-out takes a lot of time. Even if some bugs are identified at this stage, the spin of SoC result in a huge time loss and would incur a significant financial loss to the company. Therefore, pre-silicon verification is crucial, as it allows for identification of defects and their resolution prior to chip production. Simulation and emulation environments are widely used in the pre-silicon verification to verify the SoC functionality before chip fabrication. Verification is usually performed in different levels of design abstraction. The register transfer logic-based verification represented the behavioral aspect of the functionality check of an initial design, as shown in the figure 1. It takes less time to execute the test scenario and provide the design with better understanding and debug support. However, the coverage is limited, and this level of abstraction affects the accuracy of the result obtained, as it omits some intricacies of the underlying circuit and non-idealities. Physical effects represented in real circuits are not taken into consideration. Another approach is transistor level verification, in which most of the logics are designed at gate level or higher, using well-tested standard cells. However, custom logic areas are designed at the register level rather than at the gate level, which delivers some precise output of design. Though this type of verification approach offers high accuracy and detailed analysis, but requires significant effort, expertise, and computational resources. It also adds complexity to the verification process. Hence, the gate-level verification approach is used to overcome the trade-off between the mentioned level of design abstraction. As the circuit connections of an electronic chips are connections of the electronic chip are in a form of the gate. This verification is henceforth called gate-level verification, which represents the logic aspect of a design and comes after the synthesis stage. It plays a crucial role in validating the correctness and timing behavior and the physical compatibility of the design. It also helps uncover the low-level bugs, optimize the design, and ensure the proper functioning of a complex SoC. In this guide, we propose a methodology to integrate the full SoC chip level on emulation environment for complex SoCs having billions of gates. We will demonstrate a set of application scenarios executing on GLE and compare their execution time between GLE and GLS environment. Section 2. Gate-level netlist. A network or a net in a short form is a grouping of two or more connected elements. A netlist is an electrical design describes individual logic gates in their interconnections. It specifies the gates used in the circuit, their input and output connections, and logic function performed by each gate. A gate-level netlist is a representation of a design at the lowest level of abstraction. The connections between each component in the design are listed in a machine-readable file called a netlist. The netlist representation of a circuit, which is typically obtained using logic synthesis, is referred to as being at the gate level. Thus, RTL emulation is a pre-synthesis, where the gate-level emulation is post-synthesis. A complete collection list of the gates and IP models with full functional and timing behavior can be found in the netlist view, and a typical netlist representation of a circuit is shown in Figure 2. Now, Figure 2 is typical netlist representation of a circuit. The Section 3 related work. The Kruti Sundar Das, Pamidi Prakashi, and Abhimanushin Challa, and from Intel India Technology PVT Ltd, Bangalore, India, has proposed a vector-based GLE for the design for testability (DFT), like memory built-in systems, memory built-in self-test (MBIST), and automatic test pattern generator (ATPG). Pattern set in the 2021 IEEE International Test Conference India (ITC India). But others have confirmed and limited to validate DFT features only that are 2 on smaller SoC with a gate count of around 50 million. At 4. Section 4 is a GLE implementation. Implementation is prerequisite. Standard cell libraries. Standard cell libraries are represented as collections of predefined cells with their corresponding connectivity information that are used to design a complex circuit. These elements typically include cell instantiations and of different cell types, such as logic gates and flip-flops and latch. Some standard cell libraries may also contain specialized cells like multiplexers and decoders and adders and more. These libraries must be passed along with the design netlist files, failing which the compilation would fail in the front-end parsing stage. 2. Memory models. The gate-level memory models describe the behavior and functionality of memory elements using a combination of logic gates and their interconnections. These models are usually optimized for a specific technology node. The technology node affects the characteristics and the properties of the memory models, including their performance, power consumption, and reliability. Hence, the memory models are to be selected based on the target technology node to ensure it meets the performance and the power requirement. Also, the memory models have to be compatible and synthesizable with the emulation compiler. 3. Memory and physical layer PHY I/O models. RTL memory and PHY I/O models provide a higher level description of behavior and data flow across the memory element interface, double data rate physical layer DDR5, and while gate-level memory and PHY I/O models provide a low-level representation capturing the actual logic gates and their characteristics. As these models are different from the RTL to gate-level, netlist compatibility I/O models must be considered for our compilation. The actual cell delays are to be maintained in the netlist I/O models for proper read and write operations, so these models must be updated with the synthesizable logic and compatible to our emulation environment. To support scan chain testing, this synthesized netlist Models should contain the scan logics. 4. RTL2 Netlist R2N mapping report. This report deals with the signal polarity and gives the information on how the signals are connected in RTL and Netlist. It is essential to have this report for validation of any section, any scenario, and failing which leads to the undesired result. B. Implementation flow. Figure 3 is Netlist database generation flow. As shown in the Figure 3, GLE-based compilation is implemented as follows. 1. Design preparation. The design Netlist files, synthesizable memory models, and standard cell libraries, synthesizable analog models are the inputs required to generate to a design under test DUT database. Verify as memory models contain synthesizable equivalent of application-specific integrated circuit ASIC memory cells. All the analog models of the associates are converted into synthesizable models. So in the test bench, we instantiated DUT and all required transactions in SOC. So there are design primitive library files which contain cell information of a GLE Netlist. This must be given as valid input to emulator front-end process. 2. Front-end process. The goal of the front-end process is to extract the necessary information from the design source code, perform batch checks, optimizes, and mapped to the utilize the field programmable get array FPGA resources effectively. The design analysis is elaborated and synthesized to electronic design interface format, EDIF, and the relevant gates are optimized during the front-end compilation process. It is then converted to the FPGA primitive, and the detailed steps are involved in the front-end process stage as shown in the Figure 4. Figure 4 is features front-end flow. 1. Is compile. Compilation is a process of converting a hardware description language HDL such as a value of hardware description language HDL into a compilation file that can be used to program into FPGA devices. This process is crucial as it transforms the high-level design description into a specific compilation that can be programmed onto the FPGA. Elaboration. The elaboration stage improved in performance even further. It converted the RTL code into modules. This technique maps the logic-generated technology, GTAC, a technology-independent cell. It determined whether the design is compatible, and if it is not, its compilation flow is terminated. The optimization. The optimization is improved the efficiency and speed of emulation. This process eliminates the unnecessary circuits which are not banned used, and it helps in reducing the gate occupancy as shown in the Figure 5. Thus, this process aims in minimizing the hardware resources utilization while still maintaining the emulated design accurately. Figure 5 is optimization techniques. 4. Synthesis. In the emulation flow, synthesis refers to the process of converting a high-level hardware description language to lower-level representation that can be programmed in feed into a FPGA device. During the synthesis, the HDL code is analyzed and optimized to generate a netlist representation. The 5 is mapping. In this mapping stage, the HDL code is mapped to the unspecific resources available in the target FPGA device. This step determines which logic elements and the interconnection in FPGA will be used to implement the desired functionality. The 3. Backend process. In the backend compilation process, the tool inserts all the logic related to the clocking and the memory mapping. So the edit netlist from the output of the front-end process is partitioned into multiple FPGA modules. The clock. The emulation compiler identifies and analyzes the different clock domains represented in the design for handling the clocks in the big backend process. They ensure the proper synchronization, and the compiler inserts the appropriate synchronization mechanisms. It also handles the timing of the event and interrupt within the design to ensure the event occurs at an expected time relatively to the system clocks. Two is memory models. The compiler analyzes the memory architecture of the target system, and this process ensures that the memory accesses and the design are handled correctly and accurately they reflect the behavior of the original hardware. 3. Partitioning. The design netlist file is divided into the separate partitions or modules. Each partition represents a distinct unit of functionality or any component of an input file that can be executed independently. Okay, 3. Place and routing. Place and routing refer to the combined process of placing the logical component of a design onto a specific location on FPGA chips and routing the integrations between these components. 1. Placement. The placement involved determines the physical location of each logic component, gates and flip-flops and memories, and etc. and the FPGA chips. The placement step aim to assign to the components in a way that optimizes for factors like signal routing and resources utilization and performance consideration. 2 is route. After the placement step, the routing processor establishes the physical connections wiring between the placed component. It determines the routing tracks, which are the paths through which signals travel to connect to inputs and outputs of the various components. So the generated bitstream files are finally loaded into the emulator hardware at runtime. This involves configuring the emulator hardware with the appropriate setting, initializing the design, and establishing the communication with any test benches or some external debuggers. Section 5 is GLE acceleration. GLE, level emulation acceleration, the compile time acceleration. Compilation of a netlist based on design takes longer than a conventional RTL design compilation. This is because of the following reasons. First, the complexity increases the GL level design requires more computational resources and time for synthesis. The final granularity of GL level design results in a large number of components to analysis and optimize which leads to a higher compile time. The GL designs have a larger netlist sizes compared to the RTL designs. Therefore, the processing larger netlist requires more computational resources and time during compilation. Resolution. A multi-core and multi-threader support is used, which helps in saving the compile time in an emulator. By leveraging the compatibility of multi-cores and thread, the emulator can distribute the workload across them, enabling parallel processing and reducing the overall compilation time. So the figure 6 is netlist compilation time comparison. B. Runtime acceleration. And the insert of scan cells in a design can potentially affect the performance of an emulator due to the several listed factors. First, insertion of scan cells adds additional circuitry which increases the complexity and the size of the design, and thus this can lead to the slower emulation speeds. Scan cells can introduce additional flip-flops and longer signal paths that impact the critical paths in the design. Critical paths are the longest path in a circuit and determine the maximum operating frequency. Hence, it limits the achievable operating frequency. Insertion of scan cells can introduce additional clock domains and a clock requirement in the design. Ensuring proper synchronization is timing between these clocks in the emulation can be challenging, which result into degradation of the performance. The resolution. In order to overcome this and enhance the driver clock frequency, an approach wherein the flip-flops for set of test signals in different blocks of SOC are added to a sampled by the fattest design clock. This helps the compiler to improve the compile time and performance as it splits the timing path. Table 1. Compile time and driver clock frequency comparison. So the figure 7 is driver clock frequency comparison. So this increase in the driver clock frequency and less compile time after optimization techniques can observed from the table 1 and figure 1. Figure 7? Section 6. As GLE application scenarios. Loading the scan information, scan dump, from the any block or the entire directly from an external debugger, which is more reliable. Scenario 1. Switching activities interchange size format safety-based power estimation. Scenario 2. To determine whether the design is functional. Scenario 3. The Scenario 1. Another use case is scan dump of a SOC from an external debugger. This mechanism allows us to log the real scan data of an individual block or the multiple blocks through the debug port in the joint task action group JTAG protocol. Each block of the camera, CPU, and USB has its own DFT circuit, and all these blocks are interconnected to the top JTAG, and this top underscore JTAG has an eternal debug interface through which the scan data can be captured from the external debugger, which is essential in case of SOC hung to analyze and detect the malfunction of a SOC. To implement the above application scenario, the methodology as shown in figure 8 has to be followed. A. SOC scan dump capture mechanism. B. Scenario 2. A site file format used to represent the switching activities in SOCs. It provides information about the total count of each signal, which is valuable for estimating power consumption. It is vital in accessing the power consumption at different stages of the verification, thereby making the decisions for power optimizations. C. Scenario 3. Ensuring that the processor boots up the successful without any uninitialized values. This is accomplished by asserting a power on reset signal, after which the central processing unit CPU proceeds to the reset vector location to fetch and decode the instructions. The bootloader that executes and initializes the processor internal registers, memory controller, and cache. Section 7. Result. The observation with regard to the access flagship SOC is as follows. SOC scan dump capture in 54 minutes, and accurate switching activity capture in 42 minutes for a multimedia block of SOC. Basic processor boot up sequence is completed in 12 minutes. The table 2 is the GLS and GLE time comparison, and the figure 9 is the GLS and GLE execution time comparison. Section 8, conclusion and future work. A methodology flow is proposed for integrating the full SOC Netlist files to create a compiled database within the aid of an emulator compiler, and map these files on the actual hardware for complex SOCs consisting of billions of gates. Additionally, real use case scenarios like capturing the scan dump of a SOC, which is vital for debugging in case of the SOC hung, precise switching activity capture for accurate power estimation, CPU boot up are validated efficiently. As compared to the simulation that takes days to complete the verification, executing time for emulation takes only in order 2 minutes. As a result, we are able to effectively validate the long learning scenarios with a scalable Netlist enabled on a emulation environment and detect the SOC issues early during the pre-silicon stage only. There is no support for a full timing standard delay format SDF currently in emulation environment, and all the delays will be ignored by the compiler. Hence, the zero delay or unit delay Netlist files are used to validate all of these scenarios. There is a mechanism to accurately capture the prime power using a glitch generated on GPU and power emulation test bench. This will be examined as a further enhanced to emulation environment which assisted in the power analysis. In an advancement to these, we will be working on unified power format UPF enabled integrated with the GLE. This helps us to validate it or the power scenarios. Okay, thank you. I read today this paper, the Netlist enabled emulation platform for accelerated gate level verification from the DBCon 2023 India. Thank you for your time and see you next time.